Second agenda is formulation of linear programming problem. Here are 5 steps to follow. The first one is uh, objective function. We have to understand the problem and see whether this is a maximization problem or minimization problem. The goal of linear programming problems is to find a way to get the most or least of some quantity, often profit or expenses. This quantity is called your objective. The answer should depend on how much of some decision variables you choose. Your options for how much will be limited by constraints stated in the problem. And then you need to describe the objective. What are you trying to optimize? Are you trying to minimize cost, maximize production or quantities? You may have constraints like you can't spend more than $1,000 or you must ship at least 50 tons of product. These are limits but don't necessarily reflect your employer's top priorities. Don't mistake these for suggestions that you minimize cost or maximize production. Once you have done that, then you have to spell out constraints. The answer to a linear program problem is always how much of some things. What are those things? Choose variables to represent how much of each of those things are required. For example, you need to decide the variable for L, like number of leadership training programs all offered. P stands for like number of problem solving programs offered. Write these variables in your objective function and also constraints and find out which one is uh, constraint. There's a labor constraints, there are capital constraints, there are resource constraints. Those constraints you have to spell out in step 2. In step 3, you need to draw constraints. So graphically, you want to solve it. Oftentimes, when you have only 2 variables at the time, as you can see in this graph, you want to draw these constraints first and see which is your feasible region. Only when you draw constraints correctly, then you can understand where the feasible region lies. If you draw constraints correctly, that leads you to identify where feasible region is. Sometimes, it could be greater than this constraints or less than the constraints. Depending on the inequality sign, you will need to determine where the feasible region is. Step 5 is that now, when you have this feasible region, you can use ISO profit or ISO cost lines to determine where the best solution is. Or another method to use is corner point solution, where you find the corners in this uh, feasible region and plug them into your objective function. Then you will find which one is the best. So these are the 5 steps to follow when formulating linear program problem. The third agenda is graphical solution of linear programming. Um, One of the most common linear programming applications is the product mix problem. 2 or more products are usually produced using limited resources. The company would like to determine how many units of each product it should produce to maximize overall profit given its limited resources. Let's look at an example. Assume that you will produce only 2 products, either iPad or iPhone. X1 stands for iPads and X2 iPhones. With fixed resources in labor, facility, and time, you are asked to determine the efficient number of iPads and iPhones combinations. Yes, it is quite a generalized assumption. The reality is much more complicated than this. But anyway, we have only 2 items, and these are the constraints that we have. Given these constraints, for example, for producing iPads, you need 4 hours of electronics and 2 hours of assembly, and the profit per unit that you make from iPads is $7, let's say. And for iPhones, you use 3 hours of electronic for iPhone to produce iPhones, and assembly 1 hour. and the profit margin say it's $5. And you learn that you have only 240 electronic hours and 100 assembly hours. Given this information, how are you going to find the best product mix for iPads and iPhones that maximize your profit? Let's follow the steps that we have learned last time. That is first objective function that we need to form. Um, it is not that difficult because we know that it is about profit maximization. So it has to be maximize profit, right? So we need to develop mathematical relationships to describe the two constraints in this problem as well. One general relationship is that the amount of a resource used is to be less than or equal to the amount of resource available. First constraint is electronic time used, right? So electronic time available is 4x1 plus 3x2, and it has to be less than equal to 240 from a last slide that we learned. The second constraint is 2x1 plus 1x2, um, and that is less than 100 assembly time. And that's how we can um, set the objective function, and it comes to the constraints as we just discussed, right? And once you set these two constraints, then you can move on to drawing the constraints. So let us draw the constraints. And to do this, the best way that I found is that you need to find the intercepts for each equation. So set 0 for x1 and solve for x2. That will give you the intercept for x2 when x1 is 0. The same goes when x2 is 0 and x1 is solved, and then you'll have the intercept for x1 for that. And that's your line if you connect them together. And in the same way, you do that for the second constraint. So set 0 for x1, solve for x2, then you get 100. And set a 0 for x2 and solve for x1, then x1 is 50. And then you can just connect the dots like that. Then we see that 50, 100 is assembly constraint B line, that's constraint, and then electrician constraint would be 80 and 60. Since the inequality sign says it's less than equal to and less than equal to, it's below region, right? It's below region. So you shade the below the region, then it is going to be your feasible region like that. Then now you have a feasible region. The next step is that you need to use ISO profit line or ISO cost line if it is a minimization problem, and then try to move it and so that you can find where the uh, maximum point lies. So your objective function is 210 equals 7x1 plus 5x2, and you want to move this line. So you set any value over there and try to move those line here from there to here, up to the to upward and downward move around, and you will see that at this point is going to be uh, uh, maximized. So here is the ISO profit line moving, and when you are changing the profit 210 and 280 and so forth, it's going up there and again up there, and then you will see that the best point is not here or there, but in the center where these two constraints are intersecting. That's the point where it is optimized. Or sometimes you can go above that, and then that's your optimization point. So that's how you find by moving your isopropyl line upward or downward and see where the points are lying. But one hint is that the maximum point or minimum point is always in the corner, right? So either here or here, there are four corners in this visual region, and by just moving your isopropyl line back and forth, you will see which corner maximize your profit. And since you determined that this is the point where it is maximized, now you have to find how you can calculate this coordinate. That you can solve it by using substitution method, um, uh, or a subtraction method, and use that and try to set them equal and find the point where they are meeting together. And you find that the optimal solution point in the case is x1 is 30, x2 is 40. And another method is instead of using isopropyl line, you can use the corner points. Find the corners first. For example, uh, the origin 0, 0 or 0, 80 or 50, 0. And this is 10, 30. And you want to put them into the optim your objective function and see which one produces the best solution.